There's a block of limestone on the Temple Mount in Jerusalem that has been in its current position for approximately 3,000 years. It weighs between 2 and 10 tons, depending on which course you measure, and its cut face still shows the individual strike marks of the copper chisel that shaped it. The joint between that block and the block adjacent to it is less than 2 millimeters wide. A modern feeler gauge cannot be inserted into that joint, not because the gap has been filled, because the gap does not exist. The blocks were cut to a tolerance that eliminated the need for mortar on the load-bearing courses entirely. 3,000 years of thermal cycling, seismic activity, military siege, and continuous structural load, and the joint has not opened. It has not shifted. It has not been repaired because it has never required repair. The compressive strength of the lime-based mortar found in the secondary courses of Temple-era construction in Jerusalem has been tested by material scientists at multiple institutions. The numbers vary by sample, but the range is consistent, between 40 and 60 megapascals in the oldest samples, with some exceeding 70. The minimum compressive strength specification for standard residential concrete in the United States is 21 megapascals at 28 days of curing. The 3,000-year-old mortar is stronger, and it is still curing, still gaining strength, still undergoing the slow carbonation process that converts calcium hydroxide to calcium carbonate, the same mineral matrix as the limestone it binds. Modern Portland cement concrete reaches its design strength in 28 days and begins degrading within decades. The ancient material reaches comparable strength in years and continues strengthening for centuries. This is not a spiritual argument. This is a materials performance comparison conducted under laboratory conditions, with published data and reproducible results. And modern concrete is losing. The compressive strength rating that American building codes use as the primary quality metric for concrete was calibrated to a 50-year service life. Not because 50 years represents the physical limit of cementitious materials, because 50 years is the replacement cycle the post-war construction industry was designed around. The Temple Mount block was not built to a service life. It was built to a function. And the function is still being performed 30 centuries later, without maintenance, without repair, without a single documented intervention. Every concrete structure in the United States, every highway overpass, every parking garage, every residential foundation poured since 1950 was designed to a standard that this single block of limestone has exceeded by a factor of 60. That is the number. And everything that follows is the documented explanation of how it happened. Beneath the Muslim quarter of the old city of Jerusalem, accessible through a narrow entrance near the Damascus Gate, there is a quarry. Zedekiah's cave, Solomon's quarries. The name matters less than the geology. The cave extends roughly 300 meters into the bedrock, following the natural stratification of the Meliki limestone formation that underlies Jerusalem. The ceiling height varies from 2 meters to 15. The air inside is cool, damp, and still. The walls are not rough. They are stepped, ledged, scored with the geometry of systematic extraction. Blocks were cut from this stone beginning no later than the 10th century before the Common Era, and the quarry shows evidence of industrial scale production consistent with the construction timeline described in the first Book of Kings. The limestone is Meliki, a specific grade within the Cenomanian age carbonate sequence of the Judean hills. Fresh from the quarry face, it is cream white, soft enough to score with a copper tool, slightly chalky to the touch. It smells faintly mineral, like cold chalk mixed with the memory of rain on dry stone. Run your hand across a freshly cut face and it feels almost powdery, yielding, as though the stone is still deciding what it wants to become. It darkens over centuries of atmospheric exposure to a honey gold on exterior faces, developing a weathered patina that is itself a form of chemical protection, a dense calcite crust that reduces water infiltration to the interior of the block. Its compressive strength freshly quarried ranges from 35 to 50 megapascals. After centuries of surface carbonation and moisture cycling, exterior exposed samples have been measured at up to 80 megapascals. The stone gets harder with age, not softer. Harder. The material that felt yielding under the quarryman's hand becomes, over millennia, functionally identical to engineered ceramic in its surface hardness. The men who cut these blocks worked by lamplight. 1 Kings chapter 5 describes a workforce of 30,000 men organized into rotating shifts of 10,000, each group serving 1 month followed by 2 months at home. An additional 70,000 carriers and 80,000 stonecutters in the hill country brought the total labor force to 180,000 under 3,300 foremen. The archaeological evidence in the quarry supports extraction at a scale consistent with a workforce in the tens of thousands. The volume of stone removed from Zedekiah's cave alone has been estimated at over 10,000 cubic meters. The tools were copper and bronze, not iron. 1 Kings chapter 6, verse 7 states that the temple was built of stone finished at the quarry, so that no hammer, chisel, or iron tool was heard at the temple site during construction. This has been interpreted religiously for millennia, but it also describes a precise engineering protocol. Every block was cut, dressed, and finished to final dimensions in the quarry, then transported and set in place without field adjustment. Every block had to achieve dry-laid tolerances before leaving the quarry floor. The copper chisel marks still visible on Temple Mount retaining wall blocks confirm this protocol. Systematic parallel strike marks at regular intervals, a controlled finishing process. A modern stonemason using carbide tools and laser measurement can achieve approximately 1 millimeter joint tolerance on large ashlar blocks under workshop conditions. The Temple Mount blocks were cut with copper, measured by touch and line, transported by human and animal labor, and assembled into courses that achieved the same or tighter tolerances. The method was not magic. It was the accumulated empirical knowledge of a construction culture that had been quarrying and laying limestone in the same geological formation for centuries. They knew how the stone moved when it dried, how it settled under load, how much to oversize a block to account for carbonation and thermal contraction. They knew these things the way a materials scientist knows them, not from equations, but from data gathered over generations and written in the stone itself. The temple, as described in 1 Kings chapters 6 and 7, was approximately 30 meters long, 10 meters wide, and 15 meters high. Its primary structural material was quarried Maliki limestone. Its interior was lined with Lebanese cedar, imported from what is now southern Lebanon, through a trade agreement with King Hiram of Tyre, documented in both the biblical record and corroborated by archaeological evidence of timber trade in the eastern Mediterranean. The cedar served multiple functions: decorative, aromatic, but also structural in a way only recently understood. 1 Kings chapter 6, verse 36 describes a specific construction detail: 3 courses of dressed stone and 1 course of trimmed cedar beams. Repeated. This is a seismic engineering technique. The timber courses function as base isolation layers. In an earthquake, horizontal force transmits upward through the structure. In rigid masonry, that force accumulates until it exceeds the tensile strength of the stone and the wall fails. The timber courses interrupt that path. Wood compresses and rebounds. It absorbs lateral energy through micro-deformation at the timber-stone interface, distributing seismic load along the full length of the course, rather than concentrating it at a single failure point. Modern engineers modeling this system with finite element analysis have calculated that the timber courses reduce peak masonry stress by 15 to 40% depending on earthquake magnitude. Jerusalem sits on the Dead Sea Transform Fault, one of the most seismically active boundaries in the eastern Mediterranean. The builders did not have finite element analysis. They had the memory of every building that had fallen in every earthquake for 1,000 years before the first temple block was quarried. They knew what failed. They knew what stood. The mortar used in the secondary courses was not Portland cement. Portland cement would not be patented until 1824. What the builders used was lime-based mortar, and the chemistry of lime mortar is fundamentally different from Portland cement in ways that determine the entire life cycle of the material. Portland cement is produced by heating limestone and clay to 1450 degrees Celsius, producing clinker, which is ground to powder. Mixed with water, it undergoes hydration that produces calcium silicate hydrate, a rigid crystalline matrix achieving high strength rapidly. Standard Portland cement concrete reaches design strength within 28 days. This speed is the entire commercial advantage. Forms stripped in hours, loads applied in days, construction schedules compressed to a fraction of what masonry requires. But the chemistry that makes Portland cement fast makes it brittle. The calcium silicate hydrate matrix does not flex. Microcracks form under thermal cycling and structural loading. Portland cement cannot heal them. The cracks propagate, water enters. If steel reinforcement is present, water reaches the rebar and initiates corrosion. Iron oxides occupy a larger volume than the original steel. The expanding rust generates pressure exceeding the tensile strength of the concrete. The concrete fractures from the inside out. This is spalling. It is the primary failure mechanism in reinforced concrete worldwide. It is not a defect. It is the chemically inevitable consequence of embedding a corrosion-susceptible metal inside a porous, cementitious matrix. Lime mortar operates on an entirely different timeline. Limestone is heated to 900 degrees Celsius, driving off carbon dioxide to produce quicklime. Quicklime is slaked with water to produce calcium hydroxide. When applied and exposed to the atmosphere, the mortar begins slow carbonation. Calcium hydroxide absorbs carbon dioxide and converts back to calcium carbonate, the same mineral the original limestone was made of. The process takes months to begin, years to reach depth, centuries to fully penetrate a thick joint. But as it proceeds, the mortar becomes chemically identical to the stone it binds. The joint does not remain a weak boundary. It becomes continuous stone, and when microcracks form, the carbonation process heals them. Carbon dioxide and moisture penetrate the crack, react with exposed calcium hydroxide, and deposit fresh calcium carbonate that seals it from inside. This is autogenous healing, documented in samples from Roman construction to Crusader fortifications to the Temple Mount itself. The mortar heals itself, chemically, measurably, continuously. A Portland cement joint reaches peak strength in weeks and degrades in decades. A lime mortar joint reaches comparable strength in years and continues strengthening for centuries. The crossover point occurs between 50 and 100 years. After that, the gap widens continuously. At 300 years, well-formulated lime mortar is measurably stronger than any Portland cement poured the same day. At 1,000 years, the comparison is meaningless. The Portland cement has failed. The lime mortar is still curing. The decision to replace lime mortar was not made because Portland cement is superior. It was made because it is faster. The post-war construction industry prioritized speed, volume, and cost per square foot. A Portland cement foundation can be poured and stripped in a day. A lime mortar wall requires weeks of curing. In a housing market building 300,000 units a year, the difference is not a technical preference. It is a financial imperative. The older material was abandoned not because it failed, because it was slow. The second decision defining modern concrete's failure timeline is steel reinforcement. Concrete resists compression, but not tension. For thousands of years, builders managed this with geometry. The arch converts downward load into lateral compression. The corbel creates a cantilever that remains in compression throughout. The buttress absorbs lateral thrust and redirects it to the ground. These are geometrically optimal solutions, requiring no steel, no embedded metal, no corrosion pathway hidden inside the structure. Steel rebar solved the tensile limitation directly. Embedded in concrete, it allows beams, slabs, and cantilevers to resist both compression and tension, enabling the highway system, the skyscraper, the parking garage. But the advantage comes with an embedded chemical liability. Steel corrodes in the presence of water and oxygen. Concrete is porous, water penetrates. Given decades, it reaches the steel. Iron reacts with water and oxygen. The oxide occupies 2 to 6 times the volume of the original iron. The concrete cracks, more water enters, more corrosion, more cracking. A self-reinforcing failure loop called the corrosion cracking cycle. It is why reinforced concrete has a finite, predictable, and relatively short service life. The American Concrete Institute's ACI 318 assumes a 50-year service life for reinforced concrete under normal conditions. This is not a secret. It is printed in the code. The 50-year figure determines minimum concrete cover, maximum water-to-cement ratio, minimum compressive strength, and acceptable crack width. Every reinforced concrete structure built to this code is designed to begin significant deterioration at approximately 50 years. The trajectory is baked into the chemistry, 50 years. The design life of the material that replaced a system standing on the Temple Mount for 3,000. There is a moment in the inspection of any aging concrete structure when the first rust stain appears on the surface. It looks innocuous, a faint brown discoloration, often mistaken for mineral staining or runoff, bleeding through the gray concrete along a line that follows the exact path of the embedded rebar below. By the time it appears, the rebar has lost measurable cross-section. By the time the first crack opens along the stain line, expansive corrosion force has exceeded the concrete's tensile capacity. By the time a chunk of cover detaches, revealing rust-brown rebar, structural capacity is permanently reduced. This is the documented condition of approximately 56,000 bridges in the United States, classified as structurally deficient, with corrosion-induced deterioration as the primary cause. 56,000 bridges in one country, built with the material that replaced limestone and lime mortar. The economics explain the decision that materials science cannot justify. A Portland cement residential foundation costs $6 to $12 per square foot. A lime mortar and natural stone foundation built to Temple Mount standards would cost $80 to $200 per square foot, require weeks to cure, and demand masonry skills effectively eliminated from the standard labor pool. The differential is 10 to 20 times. But the 50-year service life means the foundation must be replaced at least once in the period the lime mortar version would still be strengthening. Over a 200-year horizon, the ancient material costs less, but the industry does not operate on a 200-year horizon. It operates on a 30-year mortgage cycle. Within that cycle, cheaper and shorter-lived always wins. That is not an engineering failure. It is an economic structure that has made engineering failure the default outcome. Most people watching this own a home or live in a structure with a concrete foundation. The 50-year design life applies to all of them. The clock started when the concrete was poured, and for structures built in the 60s, 70s, and 80s, that clock is at 40, 50, or 60 years. The carbonation front has been advancing inward at 1 to 5 millimeters per year. When it reaches the rebar depth, typically 50 to 75 millimeters from the surface, the protective alkaline environment neutralizes and active corrosion begins. In many structures, it already has. The pinned comment below contains a structural assessment guide. a protocol for identifying early spalling, measuring carbonation front depth with a phenolphthalein indicator test, recognizing crack patterns that distinguish corrosion damage from shrinkage, and understanding when professional evaluation is necessary. It also contains documented information on lime mortar and natural stone alternatives, now being reintroduced by firms that have studied the ancient material record. The guide is there. The data is there. The decision is yours. The compressive strength of Melicky limestone has been measured across hundreds of samples. Freshly quarried, it tests between 35 and 50 megapascals. Samples from exterior courses of the Temple Mount retaining wall, subjected to 3 millennia of weathering, test between 60 and 80. The stone indurated. Atmospheric carbon dioxide reacts with the calcite matrix at the surface, producing a dense carbonate crust that reduces porosity and increases hardness. The same process that strengthens lime mortar strengthens the limestone blocks. The entire wall, stone and mortar together, undergoes the same slow transformation, becoming denser and harder with each century, a self-improving system. The chemistry can be described as a single reversible reaction. Calcium hydroxide plus carbon dioxide yields calcium carbonate plus water. Carbonation hardens the mortar. Calcination, the reverse, is how limestone is burned to produce quicklime. The entire cycle is a closed loop. Limestone is quarried, burned to lime, slaked with water, applied as mortar, and absorbs atmospheric carbon dioxide to become limestone again. Over centuries, the mortar joint becomes mineralogically indistinguishable from the stone. Under a polarizing microscope, a well-carbonated lime joint shows the same calcite crystal structure, grain boundaries, and optical properties as the adjacent block. The joint has ceased to be a joint. It has become stone. This chemistry has a direct consequence for crack resistance. When a microcrack forms in lime mortar, it exposes fresh calcium hydroxide to atmospheric carbon dioxide and moisture. The carbonation reaction deposits new calcium carbonate in the void. The crack fills. This has been documented by environmental scanning electron microscopy in laboratory conditions and by conservation scientists studying Roman aqueducts, Byzantine cisterns, and Crusader fortifications, where mortar joints cracked by seismic activity centuries ago show complete healing. Core samples from the Temple Mount secondary courses show multiple generations of healed microcracks, each sealed by a distinct layer of secondary carbonate. The mortar has been cracking and healing for 3,000 years. Each cycle makes it denser. Each repair is permanent. The seismic record confirms the engineering. The Dead Sea Transform Fault has generated earthquakes estimated at magnitude 6 to 7 at intervals of 1 to 300 years throughout the historical period. Jerusalem has been struck by major earthquakes in approximately 760 BCE, 31 BCE, 363 CE, 747, 1033, 1546, and 1837, among others. The Temple Mount retaining walls survived all of them. The blocks have not shifted. The courses have not displaced. The cedar timber courses function by friction-based energy dissipation. The timber-stone interface has a lower coefficient of friction than stone on stone. During an earthquake, seismic force must overcome the friction threshold at each timber course. When exceeded, the timber allows millimeters of lateral sliding that absorbs energy through friction. After the event, gravity reseats the wall. The displacement is not cumulative because the geometry is self-centering. Engineers at the University of Minho, the Polytechnic of Milan, and Stanford have confirmed through computational models and shake table tests what the Temple Mount has demonstrated empirically. Timber-laced masonry outperforms rigid, reinforced concrete frames in seismic resistance measured by structural integrity after repeated earthquake cycles. The concrete cracks. The cracks accumulate. The rebar corrodes. The building is condemned. The timber-laced wall absorbs, dissipates, resets, and stands. The Temple Mount retaining walls remain the most studied ancient masonry structure in the world. The Weizmann Institute has conducted isotopic analysis of mortar samples. The Getty Conservation Institute has studied weathering patterns. MIT's Department of Civil Engineering has published research on dry-laid ashlar mechanics using the Temple Mount as a case study. The consensus is consistent. The materials were well selected. The techniques were empirically optimized. The resulting structure performs at or above modern construction by every standard except speed of assembly. Lime mortar is undergoing a documented revival. In the United Kingdom, its use in conservation has been standard for decades, but application is expanding. New build residential projects in the UK, France, and Germany now specify lime mortar for structural applications, driven by life cycle analysis that accounts for self-healing, breathable wall compatibility, and dramatically longer service life. France updated its building code in 2021 to include provisions for lime-based structural binders. Germany's DIN in 1996 includes lime mortar in load-bearing applications with compressive classifications, reflecting long-term strength gain rather than 28-day cure performance. Dry-laid ashlar is being studied as a seismic resilience model. Research groups in Italy, Greece, Turkey, And Japan are investigating interlocking dry stone construction as an alternative to rigid concrete in earthquake zones. The results are consistent. Dry-laid masonry absorbs energy through controlled microdisplacement, distributes lateral load across the wall length, and returns to geometry under gravity. It does not crack. It does not spall. It does not require post-earthquake inspection for hidden corrosion. None of this is nostalgia. None of it is a call to return to hand-quarried stone and copper chisels. It is material science, documented and reproducible, confirming what the physical evidence has been demonstrating for 3,000 years. The lime mortar is stronger. The limestone is harder. The dry-laid joint is tighter. The seismic isolation is more effective. The service life is longer by an order of magnitude that makes the comparison absurd. 50 years against 3,000. The block is still there, on the Temple Mount. Its cut face still legible, its joint still tight, its compressive strength still climbing through the same carbonation that has been underway since a man with a copper chisel set it in place to a standard no modern building code has matched. The feeler gauge still cannot find a gap. It is the same measurement it was 3,000 years ago. It will be the same 3,000 years from now. The stone was never designed to fail. It was designed to hold, and it holds. That is not a miracle. It is a material performing exactly as its chemistry predicts, and a structure built by people who understood that chemistry through the only method more reliable than computational modeling, watching what works and building accordingly for 3,000 years. The block holds, the mortar strengthens, the wall stands. The measurement has not changed. The only thing that has changed is the standard we compare it to. And by that standard, the ancient material is not ancient at all. It is the future of construction the industry has not yet agreed to build. The data is in the stone, it always has been. It is simply standing there, being measured, being tested, being compared, and winning every single time.